Good morning students, welcome back to our next class. In yesterday's class, I explained dense and separable definitions to you. Based on that definitions, today I would like to explain separable Hilbert space theorem. Okay, see the theorem statement one. Separable Hilbert space. Let H be a Hilbert space, then show that the following. First point, if H is separable, then every orthonormal set in H is countable. Second one, if H contains an orthonormal sequence which is total in H is separable. Okay, right now see the statement. H is a Hilbert space in the given conditions. Then our first point is, if H is separable, we want to show that every orthonormal set in the H is countable. Second one, H contains orthonormal sequence and which is total. So that orthonormal sequence and it is total. Then what we have to show that this H is separable. That is the second point. Here first in the proof we have to write the given conditions. Okay, see the proof. Let H be a Hilbert space. Okay. Next, our first point. What is the supposition? H is separable. So, given H is separable. What is the separable definition? H contains a countable dense subset. So that is H contains a countable dense subset. Okay. This is the separable definition. Next, we have to write the same thing, symbolic representation. We are taking that subset is the B. B is subset of H such that B is dense, so that its closure is equal to H, and this is countable also, so that B is countable. So these two lines only we are getting from the definition of separable. Okay. Next, we have to write our aim. What is our aim? To show that. What is the aim? Every orthonormal set in H is countable. So to show that every orthonormal set in H is countable. So for this, first what we have to take? We have to take one orthonormal set in the H. Later we have to show that that orthonormal set is countable. So here we are taking that orthonormal set is M. Okay. So our next line is, let capital M is an orthonormal set. Orthonormal set in H. So we took orthonormal set. Later what we have to show? We have to show that that set is countable. So our next line is to show that M is countable. Next line, to show that M is countable. Okay. For this purpose, here we have to take two elements in the M, two distinct elements in the M, and we have to calculate norm of that two elements, distance of that two elements we have to calculate. So our next line is, take two elements x comma y in the M, and that two elements are distinct, so that x not equal to y, and we have to calculate norm of x minus y whole square value. Okay, right. Norm x square formula in terms of the inner product x minus y comma x minus y. Next, here we have to write this inner product separately. So see, our next line is no change in the LHS. RHS is inner product of first variable comma first variable comma second having the minus, so the inner product x comma y. Next, with the second variable y comma x, both last variables are having the minus, so that it becomes a plus. Inner product y comma y. Now here this is norm x square minus these two are distinct elements by the definition of orthonormal set. Two elements are distinct, then the inner product goes to 0. Similarly, third term is also 0, and the last one is norm y square. Once these two elements are same, then the value is 1, so that here also value is 1. So what we got, norm x minus y whole square is equal to 2. Therefore, our next line is norm x minus y is equal to root 2. Clear? So this gives the meaning of theoretically the distance between any two distinct elements in M is root 2 units. So this is the symbolic form. Same thing, theoretically we are writing, that is the distance between any two distinct elements, both are not equal, in M. Okay, these two are in the M is root 2 units. We have to write the same thing theoretically in our next line. So write theoretically, that is the distance between two distinct elements in M is root 2 units. Okay, that is neighborhood nx of x and ny of y of radius root 2 by 3 are disjoint. So nothing but our next line is, that is neighborhoods nx, not smaller, capital Nx comma ny of x comma y of radius root 2 by 3 of radius root 2 by 3 are distinct. Mean to say here, x neighborhood is nx, y neighborhood is ny, radius of that elements are root 2 by 3. These neighborhoods are also distinct. Mean to say neighborhoods are disjoint. So in distinct you can write in brackets disjoint. Once the neighborhoods are disjoint, mean to say no common elements in these two, at the time intersection goes to empty, that is nx intersection ny is equal to 5. No chance for common elements. Since B is dense in H, meaning is, since B is dense in H, that is according to the dense definition, its closure is equal to main set H, so that B bar is equal to H. Then there is an element B, small b belongs to the capital B, so belongs to Nx and Ny. See the next line. Then there is an element B belongs to B, comma, this B belongs to Nx, and another element we are taking B bar belongs to the B, comma, this B bar belongs to the Ny. So here no chance to this B belongs to the Ny, B bar belongs to the Nx, because these two neighborhoods are distinct, disjoint. So that there is an element, there exists an element B belongs to the B, then B belongs to the Nx. Another neighborhood, another element B bar is belongs to the capital B, comma, B bar belongs to the Ny. So what is our aim here? M is countable. We can show that this condition is reverse. Mean to say, if possible, suppose that M is uncountable. Uncountable mean to say it has many number of elements. Okay. See our next lines. See the diagram once. This diagram only for your understanding purpose. No need to write in the exams. So here, which is the Hilbert space, so that this is the H. Okay, this entire is the H. Next, M is a subset of H, so that this is the subset of M, subset of H. Next, B is also subset of M. So B is one of the set in the M, so that this is the B. Okay. In this B, we are having two elements B comma B bar. See, small b belongs to the B bar is also belongs to the B. So these two elements B bar. Okay. B bar element. Next, we already calculated two elements distance x, y is root 2 units. So x, y two distinct elements. The two neighborhood of x is nx, neighborhood of y is ny. And one more thing, if you are observing from this line, small b belongs to the nx. That's why we wrote B is the common point of capital B and nx, so that in this box, and y, B bar is the common element of B and ny, so that B bar is here. X and y are only in nx and ny. So that here distance of these two elements is root 2 units. Radius is root 2 by 3. Okay, this is the diagram only for the understanding purpose. Next lines. Here our aim is M is countable. We have to show this condition is reverse, that is if possible M is uncountable, then what will happen? We will check it. Okay. See, next lines. If possible, suppose that M is not countable. If possible, suppose that M is not countable. Not countable mean to say M is uncountable. Okay. So our next line is, that is, M is uncountable. Uncountable means to say it is having many elements. So then we have uncountable many such pairwise neighborhoods. So next line is, then we have uncountable many such pairwise neighborhoods. So many uncountable many pairwise we have. Then all these neighborhoods are for pairwise elements. So neighborhoods are uncountable mean to say B is uncountable. So our next line is, so that B would be uncountable. Because now in this B, element X existed, so that these elements such type of elements, many elements are exist. At that time B goes to uncountable. B goes to uncountable means to say which is contradiction to B is countable. So which is contradiction to B is countable. So why we are getting contradictions? Our supposition is wrong. Therefore, our supposition M is not countable is wrong. M is not countable is wrong. So hence M is countable. Hence M is countable. This is the required first point. This is the required first point. Okay. Next I will explain our second point. What is our second point? If H contains orthonormal set which is total is separable. So here we are taking H contains, means to say we are taking one orthonormal sequence in the H. That orthonormal sequence is total. Using the two conditions, we have to show that this H is separable. So we are taking orthonormal set. Let set EK be an orthonormal, be a total orthonormal. Two conditions: be a total orthonormal sequence in H. So this is the supposition. Next we have to show that H is separable. So next line is, now to show that H is separable. Separable means to say we have to to show that this H has a countable dense subset. For this purpose, now we define set A. So A is equal to gamma 1n E1 plus gamma 2n E2 plus so on gamma nn gamma kn ek. Here what is the gamma kn? Gamma kn is equal to ak1 akn plus I bkn, where akn comma bkn belongs to the Q. So since Q is countable, so that automatically A is countable. So next line is then A is countable subset of H. What is the since part here? Since Q is countable, okay, so that automatically A is countable. So what we have to show that here, H is separable. Separable means to say it has a countable dense subset. We got a countable subset remaining to show that dense. So next line is to show that dense means to say its closure is equal to main set. So what we have to show that A bar is equal to H. So A bar is equal to H. For this, it is enough to prove that for each x belongs to H and epsilon greater than 0, there exists one element is in the A, B belongs to the A, such that norm of x minus B is less than epsilon, then A bar is equal to H. So next we are using our since part is EK is total orthonormal sequence in H. Then there is some n such that gamma n is equal to span of, see the next lines. See our next line. Since EK is total orthonormal sequence in a Hilbert space H, then there is some n. We are taking gamma n is equal to span of E1 into so on En. Span means all possible linear combinations contains a point. It means to say this gamma n contains a point whose distance from x is less than epsilon by 2. See the continuation. No? So gamma n contains a point whose distance from x is less than epsilon by 2. So that point is here we are taking y. Distance from y to x is less than epsilon by 2. Symbolic representation is norm x minus y less than epsilon by 2. Next line. For orthogonal projection y of x. For x orthogonal projection we are taking y is summation k equal to 1 to infinity inner product x comma ek into ek. Same thing we have to write y is equal to, okay, orthogonal projection. Next, the set of rational numbers q is always dense in the R. So here rational number is inner product x comma ek into ek belongs to the R. Okay, there exists one element is in the Q such that the distance of the two elements is less than epsilon by 2. Now we are taking this entire element is the B. Let B is equal to gamma kn ek. Okay. Then once the elements in this form, then these elements belongs to the A. So our next line is then B belongs to A. And we have to calculate norm x minus b value. Okay, see the next line. Our next line is then, so So this type of elements belongs to the B, so belongs to the A, so that then B belongs to A, and we have to calculate norm x minus B value, and norm x minus B is equal to, here we are adding and subtracting summation over k, inner product of x comma ek into ek. So norm x minus summation over k, inner product x comma ek into ek. Okay, we are adding and subtracting, so that here plus summation over k, inner product x comma ek into ek minus b. Then no change in the equation. We are adding and subtracting. Now norm of a plus b is less than or equal to norm a plus norm b. So less than or equal to norm of x minus summation over k, inner product of x comma ek into ek plus norm of summation over k, inner product of x comma ek into ek minus b. Now these values are nothing but from this one. See, x minus y is nothing but summation over k, inner product. So we got the same thing, x minus b. So the value is less than epsilon by 2. This one is also less than epsilon by 2. So what we will get, value is less than epsilon. So here what we got, norm x minus b is less than epsilon. See, in the above lines, instead of a bar is equal to h, it is enough to show that the condition norm x minus b is less than epsilon. We got the same thing, right? Then a is dense in the h, nothing but h is separable. See the next lines, we'll write the conclusion. That is, for each x belongs to h and epsilon greater than 0, same thing we have to write a symbolic theoretically. That is, for each x belongs to h and epsilon greater than 0, there exists b belongs to a, such that norm x minus b is less than epsilon. So then a is dense in h. Therefore a is dense in h. That is, a bar is equal to h. So in above lines we already got a is countable subset of h. Now we got a is dense in h. So next line. Therefore a is countable dense subset of h. So h is contains a countable dense subset, then h is called separable. So next line is, hence h is separable. This is our required condition in the second point. So in this theorem, completely based on the separable definition, so that if you know the definition of separable, you can easily understand this theorem. Otherwise you cannot understand. Okay, easy theorem and important for 6 marks. Out of these two points, one for each for 6 marks, otherwise complete theorem for long answer. In this theorem, that diagram is not necessary in the exams. I given for you only for understanding purpose. No need to draw in the exams. From the diagram, you can easily understand what is the distance of the 2 points, how the neighborhoods nx, ny are distinct. For understanding purpose only, I gave this one. Okay, Rama? With this theorem, our topic total orthonormal sets and sequences completed. In the next class, I will start our next topic, representation of functionals on Hilbert spaces.